Yeah. So in case you don't know me, I'm Wei. I work for Citrix for the Zen platform team to help make Zen better. And this presentation is a joint work by me and Elena. Actually, she did all the heavy lifting job, like writing the code and patches. And I do the easy job for writing the presentation, running some benchmark, and flying across the Atlantic and get grilled for 30 minutes. Yeah. So vNUMA. It's actually not a very new topic, so I'm going to rehash it here today. So vNUMA is short for virtual NUMA. So this project actually aims to export the virtual memory topology to the guest. And this virtual memory topology can be configured as the admin sees fit. So the most useful use case is that you can configure vNUMA, this virtual memory topology, to match the underlying machine memory topology so that the guest can achieve the best performance possible. Yeah, so let's go straight to our topic. So here is the agenda of my talk. I'd like to first talk a little bit about the motive about this project, and then give a brief overview of the history and current status. And then I'll also go briefly into the design and implementation sort of things. I'll also talk a little bit about the problems I've discovered so far, and also then go into the very preliminary benchmark results. So some of the results are very weird or interesting to see, but I'm an honest person. I've just put it in here and let everybody know about the current situation. And finally, just talk a little bit, just list some to-dos on my list so we could hopefully get something done in the 4.6 or in the future releases. So for the motives part, well, I don't need to emphasize this anymore because cross-NUMA no memory access is considered very expensive, and though I don't have any, I haven't done any micro benchmark to prove it, but I guess everybody knows it. I just don't bother doing that. So actually, we would like to have the guest to avoid cross-memory access as much as possible. And then, as the hypervisor is actually NUMA aware, so it knows the underlying memory topology, and so that it can do NUMA aware scheduling and also NUMA aware guest memory placement. And operating systems like Linux is also NUMA aware. So when it also has features like NUMA aware scheduling and also memory allocation and migrations, so that, well, it knows how to optimize the workload. However, the missing bits, though there are certainly some missing bits in the bigger picture, that is, currently Zen is not able to provide a memory topology map to the guest. So when you create a guest, no matter how many NUMA nodes it crosses, it just gets a single node from the guest point of view. In some very weird cases, I mean extreme cases, well, actually many HPC or some memory intensive workload actually hampers the performance very much, and then you can see that in my benchmark later on. And also, yeah, the other missing bit is CPU topology. So with these two missing bits fitting in the gap, we can have the guest able to make use of underlying memory, as efficient as possible. And yeah, as I said, this is by no means new or cutting edge features. So around 2010, actually ideas and patches were tossed around in conference and on the mailing list. But well, it's a pity that neither of them was properly upstream. Fortunately, Elena started to work on this as an OpenW intern back in 2013, and she keeps working on it and keep improving it. And last Saturday, she posted V7, yeah, right? V7 of a patch series, yeah. So I would like to thank her for her hard work and for this project. Actually, I did this benchmark on one of her versions. Yeah, we'll see. Let's go to the design. The design is actually quite simple. For the PV and PVH, we need to make use we need to make use of the PV interface. So actually, toStack puts some enlightenment information in the hypervisor, and then arrange Zen to allocate guest memory in accordance with the enlightenment information. And then when the guest boots up, it just retrieves that virtual memory topology layout via the hypercores, and then builds its own memory map. As simple as that. And yeah, as you can see, this is the enlightenment information structure used in the hypervisor. So we store the number of nodes, virtual nodes in NRV nodes, and then we have a two-dimension arrays that used to store the distance among nodes. And then vCPU to vNode is an array that stores the CPU to node mapping from guest to point of view. vNode to pNode is an array that stores the virtual node mapping to the physical node mapping. And this array is actually useful when we need to do NUMA-aware ballooning. We'll get to that later. And then vMemory range is yet another array to store the memory range for different virtual nodes. And for HVM guest, the whole procedure is more or less the same. So first, toStack passes the configuration file and generates some enlightenment information. Then it puts it in the hypervisor. And then it arranges some active tables in the HVM loader. And then the hypervisor will allocate the memory in accordance with the enlightenment information. And then finally, when the guest boots up, it retrieves that information via active table. And then builds its own memory map. As you all know, showing some active structure is not very interesting. So I'm going to skip that. However, if you ask me if there's any problem with vNUMA and all the other memory-related features, I would say, well, there's certainly some problems that I've seen so far. In case you don't know what POD means, it's POD, populating on demand. So is that when you put up an HVM guest with memory less than the max amount of memory it can have? So this is a mechanism. So the hypervisor actually allocates a certain pool of memory. It shuffles it around as the guest boots up until the balloon driver kicks in. So for pguest, making vNUMA work with ballooning is actually quite easy. As you can see, it is structured. We have the vNode to pNode mapping, so that from pguest point of view, it actually knows what pages does this the mapping between pages and physical nodes. So when it tries to increase its reservation, it can just make use of the information get in that array and then make the hypercore to ask for pages from specific node. So so this is quite easy. And pguest doesn't need POD support at all, so that's an NA here. For HVM guest, it's a different story. As I said before, the POD is active until balloon driver kicks in, and this imposes there's three major difficulties in this work. So first, POD itself is not NUMA aware at the moment. So when it shuffles pages around, it actually messes with the memory mapping a lot. So in order to make POD work with vNUMA, we need to do some weird dancing or trick in the hypervisor to keep track of the moving pages. And ballooning, well, because it doesn't make use of the hypercore, it doesn't know the virtual node to pNode mapping, so that it can't effectively request pages from specific nodes. Well, this might be, I might be able to solve this with some self-invented active table. Well, but I'm not sure because I haven't gone into the active menus yet. So, and it's open to discussion. And the third thing is that HVM loader is allowed to move memory around under certain conditions. This also requires some bookkeeping in the hypervisor. So in all, these three difficulties basically makes vNUMA unable to work with these two features. And the fastest path to make HPVM have vNUMA feature is that to make vNUMA actually mutually exclusive to the other two features. So, and for the upcoming PVH guest, I put the Y star in the ballooning, ballooning slot, because as of the time I wrote this talk, PVH guest is not able to book with ballooning enabled due to some rough edges. Well, but it's not a big deal. Well, in theory, it should just work because it's taking the same path as PV guest. So I put this Y star here. As for pod, it's still unclear whether PVH guest should use pod at all. And I think it's currently being discussed on Zendewell, so I just put a question mark here. Another somewhat orthogonal and minor problem is the CPU topology. So on the left-hand side, that's the CPU topology map inside a guest without vNUMA. And on the right-hand side is the CPU map with vNUMA. And below it is, this is some kernel debug message complaining that the CPU topology is not sane. So this might be a problem at some point because the guest scheduler might not be able to make the right decision due to the fact that there isn't a proper CPU map. Well, but yeah, as I said, it's somewhat orthogonal to this vNUMA memory layout work. But I would like to just list it here anyway. Okay, time for some benchmark. So here I have a host with 2 sockets, 12 pCPUs, and HT disabled. And also it has 36 GB of RAMs and split equally into 2 NUMA nodes. And in the host kernel, NUMA balancing is enabled. As for the guest, it has 12 vCPUs, 16 GB of RAM, and 2 virtual NUMA nodes. And those 16 GB of RAM is split equally into 2 nodes. And also, each vNode is mapped to different P nodes, like vNode 0 to P node 0, vNode 1 to P node 1. And the vCPUs ping to the corresponding P nodes to achieve maximized performance. And also, vNUMA balancing is enabled in the guest kernel. So far, I've run 3 benchmarks. One is Autonuma, which is in essence a bunch of threads accessing global or local memories. And the other one is SPECJBB, which, well, I don't think I need to introduce anymore. Yeah. And the last one is Stream, which does some very basic operations to measure memory throughput. And here is the result. So for the Autonuma benchmark, this is NUMA 0 benchmark. It creates 12 threads to run freely in the guest. So it's actually up to the guest scheduler how these threads can be scheduled or to run on which node. So as you can see in the chart, so PVH is actually doing quite good and achieve near native performance. However, the PV guest with NUMA balancing enabled actually does a little bit worse than PV guest without NUMA balancing enabled. This is due to the fact that NUMA balancing involves lots of page table operations, which is quite expensive for PV guest. So when it tries to migrate the page, it needs to map a page from a node, then map another, and then copy contents around. So it's a little bit expensive for PV guest. Yes. Oh yeah. Right. So unless I note it here, so all the other configurations have NUMA balancing enabled.
All 3 virtualized cases, that's all with vNUMA.
Yes.
Yeah. How does that compare without vNUMA?
I forgot to mention. Unfortunately, this benchmark won't run on a single node system. The purpose of this benchmark is to see if exposing a sensible memory topology to the guest, so that the guest can achieve some near-native performance. Yeah. Yeah. And then, so when it comes to the NUMA 0 hard bind benchmark, and it goes a little better because this hard bind actually means you bind threads into a specific nodes. So actually, there's no memory migration involved anymore. So in this case, so the PVVM with or without NUMA balancing actually achieve the same result. Yeah. Again, but PVH is quite stable in this benchmark with near native performance. So in brief, exposing a sensible memory layout to the guest can help the guest to achieve near native performance. And NUMA 02 is a different benchmark that tells a different story. It actually rewards page migrations. So this benchmark actually starts with all memory allocated in one node. Then half of the memory will be gradually migrated to another host. So this, in this case, you actually have a better result in the PVVM with NUMA balancing enabled case. And this chart actually depicts the penalty that cross-node memory access for PV guest is actually quite expensive. It's making the, so yeah, it's actually like 40% worse than without the memory migration. Another benchmark, so this is SPECJBB, which is very weird. So for the PV case, you can see the cross node with vNUMA is achieved the best performance in 3 cases, while the cross node no vNUMA benchmark gets the worst result. That's kind of expected because, well, cross node memory accessing, well, is just bad. While in the PVH case, exposing the underlying memory topology actually makes things a lot slower. Yeah, it actually doesn't quite make sense. And the cross node no vNUMA case actually is the farthest of, is the best of those 3. No, that doesn't make sense. Well, I guess there's might be some bugs somewhere in the PVH case that needs to be sorted out. Well, but not now. I've played with some. I've too many things. It's like I mess around with the pinning. I mess around with CPU map. I mess around. Yes, because PVH won't work without EPT. Yeah. You mean what? Sorry? Yeah, but yeah, unfortunately PVH won't work with shadow. But it still wouldn't, it still won't explain why exposing the virtual memory layout actually makes things slower. Yeah, so it's just weird. Yeah, actually, I'm looking forward to Boris' VPMU patch series so that I can properly profile this whole process and to find out where the bug is. Yeah. So another configuration is that I run 2 JVM instances on 2 nodes, and the results aggregated. So for PV, it actually follows the same pattern. Though the gap is a little bit smaller, but it still follows the same pattern. And for PVH, yeah, it still follows the same pattern. Cross-node vNUMA, well, sucks. Sorry. Need to sort it out at some point. And the final, the last benchmark I ran is Stream. Well, it's just a very simple benchmark to do some very simple memory operations like writing, multiply, add, something like that, and to measure the throughput. And PVA, vNUMA makes a very huge difference here. As you can see, enabling vNUMA makes things like 70% faster. Yeah, so it's actually quite impressive. Okay. Conclusions. vNUMA improves performance for PV guests. And then vNUMA gets some very real result in SPECJBB. Yeah, the other two benchmarks have very good results. Well, it's a pity that the benchmark that most people care about sucks at PVH. Yeah, I would like to say. And then here are some future works. So we would like to have some very basic vNUMA supporting for all gas types in the near future, probably in the 4.6 window. By basic support, I mean upstreaming the PV interface for PVH and PV, and then get the basic HVM case to work. That is to need to disable port and ballooning when you enable vNUMA. That should be easy. And then we would also like to have some support in DOM0 vNUMA. This will be based on the very basic vNUMA support. So with DOM0 vNUMA, you can actually separate DOM0 memory into different NUMA nodes, and then you can ping the backend threads and routines to that node so that it can achieve better performance by avoiding ping-ponging between different nodes. And then we probably need to address vNUMA compatibility issue with port and ballooning for HVM guest. Yeah. But I don't know whether people care much about this, because if they want to use vNUMA, they probably aim for performance instead of saving memory. I don't know. We'll see. And then we'll need to address the performance issue for PVH. This should be done after Boris VPMU patch release goes in. So okay, yeah, that's all for my talk. Questions? I think it's the latter. Gas won't work in optimized way. Yeah. Well, because basically it invalidates the meaning of vNUMA, because now your underlying memory is actually scattered in different, spread across different nodes. Yeah. Any more questions? Yeah. Yes. There will be change in the tool stack. Okay. You're actually looking for okay. Libvirt API. Okay. Yeah. Okay, we figured it out.
With the SPECJBB test you did, how much were you maxing out, or were you maxing out the CPU capability on the machine? Were you using all of the pCPU?
Yes.
Okay, and 100% or very high?
Yes.
Do you have any kind of feeling as to how much of the QPI bandwidth you were using?
No, I haven't done anything to measure that.
The reason I'm asking, I'm wondering if the benchmark's getting to the point where it's actually suffering from contention on the interconnect, or whether there's, because we know the QPI is pretty decent, I think I would say. So I'm wondering if it's actually the point where there's not enough traffic going across to actually hit the point where you get the real advantage from vNUMA.
Right. Yeah, that's a valid point. You need to figure out.
The extreme ones you clearly were.
Yeah.
Maybe the JBB one is less heavy.
Yeah. That could be. Yeah. Still need to do some proper profiling to answer that question. Yeah. Well, that can be certainly done because, well, we don't actually prevent you from shooting yourself in the foot. Say that. But that's also a valid use case because when you migrate a guest from the from a host with many nodes to a single NUMA node host, well, that will work. Yeah, then you would need to maintain the mapping somehow in the two-stat or the migration stream. Yeah, I think that's doable. Yeah. And whether that's a good idea or not, I don't know. Okay. Yeah, I think that's definitely doable, and I think you. What? I'm not sure. Just asking. Oh. Okay, yeah, we'll test that when we implement the things. Okay.
So back to the SPECJBB EPPH case, did you check how tables are?
It's 4K pages.
Yeah, and then where are they basically?
Oh, I haven't checked that.
It can be random, or
Yeah.
same DOM 0, no 0, or how do we know that you provided, showed it to the guest?
You mean the memory size of the guest?
Yes, yeah.
It's 16 gig
No,
per byte.
no,
Oh, 8 gigabyte each.
and how many?
Two nodes. Yeah. That maps to the underlying machine layout. Yeah, the machine also has 2 nodes.
So to your question, Jen,
So EPP page table itself can be on node 0 or node 1.
Oh yeah.
not the actual pages.
Because,
Right.
like somebody pointed out, in the SPECJBB case, it's very clearly mentioned. Okay. So every time you had a TLB miss, then you need to go through the guest page table and then EPT page table.
Yes.
Right?
Wow.
So,
Oh, that's a very interesting point. Yeah. Thank you. I don't think DOM 0 matters that much because it doesn't actually do anything.
I think Jun's question is something that's really worth discussing
Right.
on the next. I think Dario probably has something to say on that.
Yes. That's
That's
a very good point.
That's the issue, actually.
And thank you. Yeah, that's a very good point. So any more questions? No? Yeah, then let's go to the party.